So this is probably the last video for chapter 17. The big topic in this video is going to be about solubility of different compounds. If I look at the PowerPoint that's for chapter 17 part 2 on the shared class files, it starts out talking about heterogeneous equilibria to kind of review a little bit of chapter 15, where when we write a reaction out and we're doing equilibrium constants, we only include aqueous and possibly gaseous molecules. Anything solid or liquid gets left out. That's fundamental for writing equilibrium constant expressions in this chapter. So specifically what we're going to be talking about, I'm going to pick up on slide 4 of the PowerPoint, is the solubility of compounds in water and how we can calculate the amount that can dissolve based on the equilibrium constant. This is the point where we kind of have to admit that earlier in chemistry in 1211, there are cases where we overly simplify concepts, sometimes a little bit of a lie that we tell you guys to keep us moving through material until we're ready to handle more complicated topics. So chapter 4, we made you guys memorize the solubility rules for ionic compounds. We learned that most ionic compounds are soluble, some are insoluble. We learned rules like if we have an ionic compound that contains chloride, chloride compounds are mostly soluble unless you combine the chloride with silver, mercury, or lead. So silver chloride is considered to be an insoluble compound based on that rule. That's not true. Actually, silver chloride is a compound that has a fairly low solubility, so that if you dump silver chloride in the water, a tiny little bit dissolves, but not very much. Okay, and then that is an equilibrium process where once you have a saturated solution, if silver and chloride ions in solution come together and form a precipitate, another particle of silver chloride can actually dissolve, and you can have things coming out of solution, going into solution constantly. But once it's reached equilibrium with a saturated solution, the total amount of silver ions and chloride ions in the solution will remain consistent. Okay, that sets up this area of chemistry that we're talking about, which is solubility product, where we write out a reaction for the dissolving of a compound, which should look something like the one I have on the board. Lead to iodate reacts, it's a solid. If it's added to water, some of the compound will dissolve into solution, which can be represented as a chemical reaction. The ions do come apart, so I have lead plus 2 ions in solution and iodate ions in solution. It's a 1-to-2 ratio. So when we write this reaction, anytime we're talking about solubility of compounds and we're going to use a Ksp value for the reaction, we have to write the reaction in this form. You have to put the solid on the left side, the dissociated ions on the right side. Even though equilibrium reactions can go either way, the Ksp is specific that it has to be written the right way for the value to actually make sense. So the first problem on the PowerPoint on slide 4 says when lead iodate is added to water, a small amount dissociates at 25 degrees Celsius. The lead concentration that results in the solution is 4.5 times 10 to the minus 5 molar. Calculate the Ksp value. So this is a reaction. It is equilibrium. The equilibrium constant is called Ksp. It's referred to as the solubility product constant. We want to solve for that value in this problem. There will be other problems where the Ksp is given, or sometimes you need to look it up. It's in the same table in your appendices of your book as the Ka and Kb values. There's a separate table in there for Ksp values. Okay, so anytime you're working on these problems, you may have to look up those numbers. This number is probably in the table, but we're pretending it's an unknown and we're going to solve for it. So equilibrium, we're going to set up an ice table. Ice, baby. As we work through it, we have our solid, which is not really an important part of the table, because when we set up our expression, the solid is not going to be part of it, but it's important to kind of understand how everything fits in. So if I have a beaker of water, I dump in some lead iodate, I need to dump in enough lead iodate so that the amount that dissolves will saturate the solution, and then usually you want to have some solid left over. So the key here is the amount of lead iodate is not important, other than it needs to be at least enough to create a saturated solution. So I'm just going to throw a C there for some concentration of that has to be added, but the value is not overly important. It just needs to be above some threshold. Okay, but the key, when it dissolves, the amount of the solid is going to decrease by a specific amount. Sometimes we're going to put X right here, like it'll be C minus X. That represents the amount of the compound that dissolves. That's often referred to as the solubility of the compound. It's usually wanted in molarity, so sometimes we call it the molar solubility. It's the amount of a compound that can dissolve to create a saturated solution. Now on the other side, we start out with 0 lead and 0 iodate, assuming that we have pure water initially. So I'm going to go ahead and fill in my initial values, both those at zeros. And then, as I said, the amount that dissolves here, it's a 1 to 1 to 2 reaction. So if this was X, this would be X, this would be 2X. I would subtract on the left side, I would add on the right side. Okay. On this problem though, they actually told me the equilibrium concentration of the lead ends up being 4.5 times 10 to the minus 2. So if I know the initial lead is 0, I know the final lead is 4.5 times 10 to the minus 5 molar. If I know those two values, then in that case, I don't have an unknown in this table. I have enough information that I should be able to solve for all the values. So 0 plus, it has to be that number, 4.5 times 10 to the minus 5. That's the amount of lead that was produced. It's a 1 to 2 reaction. So that means the iodate, it should be twice that much in this position. So 2 times 4.5 is going to give me 9.0 times 10 to the minus 5. Therefore, 0 plus that number, my iodate concentration ends up being 9.0 times 10 to the minus 5 molar. My lead iodate, I do know that the amount that dissolves is 4.5 times 10 to the minus 5. But honestly, it's the solid. When I set up my expression, this column is not going to be important. So I've got my numbers now. Ksp equals the lead concentration, which is 4.5 times 10 to the minus 5, times the iodate concentration squared. Remember, the 2 is going to make me square that concentration. So the iodate concentration is 9.0 times 10 to the minus 5. And then I do need to, if I erase that number, I need to square that value. That's going to give me my Ksp if I multiply that out. And I'm going to leave that to you to do. Punch that in. Just don't forget to square your IO3 value. Okay, so if I go now to the next slide, have another problem on the next slide. This is slide 5 now. It's pretty similar to this one. Really, the only thing that changes, instead of lead iodate, now I have barium iodate. And this time, in this problem, they give me the value of Ksp, 1.5 times 10 to the minus 9. And with that value, they ask me for the solubility of the barium iodate. Again, what the solubility means, they're asking how much it dissolves. That means if I have some amount of barium iodate that's dumped into a solution, minus X, if I can solve for that X value, that's the solubility. Specifically in molarity, which is, that's the default unit that we use unless they ask for it in some other type of unit. Okay, so if I have some amount of barium iodate, I lose X here, it's 1 to 1. I should gain X here, and then I'll gain twice as much IO3. I'm going to gain 2X under iodate. So again, the solid doesn't really matter, other than it sets up the basis for the equation. I end up with X of barium, 2X of iodate. So now I can set up my Ksp. Ksp is 1.5 times 10 to the minus 9. Equals, the barium concentration is X, the iodate concentration is 2X, and then that's squared. Now, that's my setup All I need to do at this point is solve for x. A couple key things here. 2x squared. Don't forget the squaring, you have to square the 2 and the x, so that's going to end up being 4x squared times x. So this is going to equal 4x cubed. So then to solve for the x value of x, then divide by 4, take the cube root on my calculator. That's the key. Sometimes I have students that when they get to the test, they haven't ever done a problem where they took the cube root, and often that can be very upsetting on a test if you can't figure out how to type it in. So make sure you've practiced taking a cube root, and even you could have an x to the 4th, which means you could take the square root twice. You could have a x to the 5th and have to solve for the 5th root. Make sure that you're able to do that on your calculator. Okay, so that's it for that problem. Move on to the next one. All right, so the next problem in the PowerPoint is actually very similar to the one we just did. It asks for the solubility, ask you to find the solubility product, which is the value of Ksp for silver sulfate. So things to watch out for: silver sulfate, it doesn't give you the formula, so you have to remember sulfate's -2, silver's +1, so the formula should be Ag2SO4. When it breaks up, it'll give 2 silver ions and 1 sulfate ion. After that, when I start setting up my ice table, it gives me the solubility, which is the value of X, but it gives it to me in grams over milliliters. You need to convert that into molarity before you set up the table. Otherwise, the math is pretty similar to what we've already done, so I'm going to skip over that problem and get into another one that is different from what we've done. So the next topic in there is solubility product. With solubility product, not solubility product, it is common ion effect. With common ion effect, we have a solution where we're dissolving a compound, but then the ions that are in the compound I'm dissolving, one of them is already present in the solution beforehand. Okay, so we're going to do a problem. It's actually the problem on slide 8, where silver iodide solid is dissolved to form Ag+, Aq, and I-. Right? So if I set up my ice table, again, I have some amount of the solid, I dissolve X. Usually if I was setting this up, if I were dissolving this compound in water, the initial amount of Ag and I- should both be zeros. This one's different though. They're not zeros because I'm not dissolving this compound in pure water. I'm actually dissolving a solution that is 0.1 molar sodium iodide. It's very important. When you read this problem, it mentions 2 different compounds, the silver iodide and the sodium iodide. You have to recognize that the reaction you write has to relate to the insoluble compound. And we know that because that's the Ksp value they gave me corresponds to the silver iodide. The sodium iodide is a very soluble compound. It's already present in the solution, and I'm trying to add the silver iodide to that. Okay, so what happens is the initial amount of iodide in the 0.1 molar sodium iodide solution, there's already 0.1 molar iodide in that solution before I've even added this compound. So my initial amount of I- is going to be 0.1 molar. Now, why is that important? Well, if you remember Le Chatelier's principle, if this reaction went to equilibrium, normally there'd be a certain amount of the ions on the right and a certain amount of the solid on the left. If I add more of one component, it's going to shift the equilibrium back the other way. So basically, if we have iodide already in solution, that's like adding extra iodide into the solution. Equilibrium is going to shift back to the left toward the solid, which means it's going to lower the amount of the compound that can dissolve. So having a common ion in solution will lower the solubility of any given compound. Now, to finish the problem, there is no, in sodium iodide solution, there's no silver in there, so my initial silver is going to be 0. But then I'm going to have my shift, minus X over there, plus x here, plus x here, giving me x and 0.1 plus x. Now, if I set that up, Ksp, which for this one it gave me Ksp is 8.5 times 10 to the minus 17 equals x is my value of silver, but then for my iodide, if I plug in 0.1 plus x, I'm going to have a quadratic. It's another place where I want to simplify if I can. I don't really want to do a quadratic because that takes a lot of time. The amount of iodide I start with, 0.1 molar, is a fairly high concentration. The amount of this compound that's going to dissolve would normally be small, and with the common ion effect, it's going to be even smaller. So I'm pretty sure that the plus x that's being added is going to be insignificant compared to the amount I started with. With the common ion effect, that is pretty much always going to be true. So I'm going to take my 0.1 plus x, I'm going to drop off the x value, and it's going to become 0.1. So I'm going to have Ksp equals x times 0.1. At that point, I can divide. My x value is going to be 8.5 times 10 to the minus 16. If I compare that to the solubility in water, which is actually given on the slide, it shows that the common ion effect lowers the solubility of this compound from 10 to the minus 9 is what it's supposed to be, to 10 to the minus 16. That's a huge factor of decrease.